Hello? Okay. So again, good morning, and I want to thank you all for coming to the seminar today. My name is Yizhak Bot, and I am the president and the CTO of BQR from Israel. And I want to thank DSO, Mr. Chua Peng Seng, his staff, and Mr. Yeo K. Kong, Director of Quality Division of hosting this day. I want also to thank Mr. Lee Yo Ling, our distributor in Singapore. I will sit the rest of the seminar. It will be difficult for me to stay the whole day. Okay, so I will start with an introduction before I go into the modules. And the day is split into 4 modules, starting with RAMs and ILS, basic understanding. Sorry. No. Yeah, okay. I need to synchronize it. Right. Okay, so I will. The day will split into 4 modules, starting with RAMs and ILS, basic understanding, parameters, and type of analysis. The second module will cover the MTBF prediction for electronic and mechanical parts, which is the basis for all RAMs and ILS engineering. The third module will cover RAMs analysis types, and the fourth will cover the ILS part. I will use a sample product to demonstrate the various analysis and results. And I will use also software which we developed in order to make it more visual. I try to combine in one day tips with a different view of reliability and maintenance for people who are already working in this area. And for people who are new to this area, some lights to help understanding the ELITIS topics. And by ELITIS, I mean reliability, maintainability, testability, and so on. We introduced, in the last 5 years, we conducted several seminars like that, mostly in Israel, but also in other places such as Netherlands, UK, Slovenia, and now in Singapore. In the seminars, we are trying to introduce new methods and techniques. Before we go into the details of the modules, I want to tell you a little bit about our company. So we are an Israeli company located in Rishon LeZion, which is about 10 miles south from Tel Aviv. We established the company in about '89, and we started as a consultancy for RAMs and ILS. And you see what are the abbreviations, all those ELITIS. And we performed until today more than 2,000 projects for over 120 customers. During that time, we have developed software to help us with the consultancy. We package the software as off-the-shelf tools. And today, the main business is to sell the software and distribute it. And of course, we continue doing project consulting to support our software packages. Last week, we introduced our new website, which shows you the BQR solutions for product lifecycle. And we are starting from the design. And you can see from design, the BQR solution service. So when we start from the design, you have CAD tools like Mentor Graphics, Cadence, OCAD, Zukin Redac, AutoCAD, and of course Excel sheets. This represents the design. We have interfaces that capture the information and the data from the CAD tools. So the first step is for electronic products. It's a fixed stress, reduced stress, and reduced risk. It's analyze the circuit for mistakes, errors, and stress simulation. Then second module is the CARE, a traditional reliability analysis tool, which have several modules. Then we continue with the APM optimizer, which is an expert system for optimal maintenance. And the results, it's been the optimal maintenance concept and all relevant reliability data goes into the ERP and the EAM in order to continue maintaining the product in the field. So you can see that we support from design to service with a full set of tools that helps you to improve the reliability and the maintenance of your products. If we look into the fixed trace, it has several modules, like the schematic design analysis to detect errors. Every module I will introduce later by an example that will show you how it is used and how it will improve your design. Electrical stress simulation, electrical stress derating, thermal analysis, operational MTBF and service life prediction, and of course PDM library integration to reduce the time effort to build up the libraries. If we look into, on the left side, the care, it has several modules, and in addition to the electronic circuit that the fixtures can analyze, the care can analyze also mechanical systems, mechanical designs. So it starts with MTBF prediction for electronic and mechanical parts, electrical stress derating, fault tree analysis, failure mode effect and criticality analysis, testability analysis. This means the ability of the circuits to detect and isolate failures to the root cause. Reliability and redundancy block diagram, which represent the reliability model of your product, including the redundancies in the structure, in the picture. Mean time to repair, safety and risk analysis according to IEC 61508. And it supports also a simple module for mini ILS and LASAR. The APM optimizer, it's asset performance maintenance optimizer, starting with the RCM, reliability centered maintenance, lifecycle cost, field replaceable unit strategy, and level of repair analysis that look like the same. Preventive maintenance optimizer, mechanical reliability simulation, which is very important to support the mechanical parts in a system. A predictive inspection optimizer, sparing to availability, resources to availability. Maintenance steering groups is MSG3 for aircraft, and the field data analysis and reliability. You can see that our company involved in a lot of industries, starting with aerospace, aviation, automotive, transportation, chemical, electronics, defense, military, power, energy, plants, gas, oil, and medical. You can see some of the logos of the companies that we are working with. Some of them are smaller companies. Some of them are huge companies, like IBM, Cisco, Siemens, Philips, Bombardier for the train, Alstom, Schiphol, the airport itself, and others. I will give you a few seconds to browse into that. Okay, now I will start with the module A, RAMS and ILS overview, parameters and analysis type. What I tried to do in this seminar is to combine all the requirements, all the parameters in one session, which is short, to give you some guides in the future that will help you to use them in your projects. So this is a general structure of a company from the management view. So we are all working for companies, and what companies want is to make money by being the leaders in their business. It means to produce the best product. If they have the best product, they will make money. And what company needs to be successful is a customer with a need and a product that addresses this need. There are two types of voices in a company. The customer voice, which is presented by the marketing and sales, and the product voice, which is presented by several departments, such as engineering, QA, RAMs, production, and customer service. So if we take the customer voice, which is presented by the marketing, what the marketing want. They want to have a product which is cheap, do a lot of functions, reliable, and easy to maintain. For example, if they will have a vehicle that goes to the moon in 5 minutes, which costs $10, they can sell a lot. Everyone wants to buy such, so they can make a lot of money. But life is not so easy. So products are complex, expensive, and we need to work to develop them. So from the other side, we have the product and the design voice, which is presented by those departments. So we have the engineering, which represent the product spec, the design spec. They want to develop the state-of-the-art product, use the best design tools, but what they are missing, or what they need also, best verification tool. They can design the best product, but they need also to verify that this product is following the specs. What is the QA and RAMs targets? Define the target. What will be the reliability? And what will be all those ELTs and numbers, how we make sure that the product meets those reliability and maintenance target from the marketing. So they need to have a design QA process. It's mean how to evaluate the design during the design phase, how to evaluate the production process. They need data for statistics, a lot of data, because if they don't have statistics, it's difficult to follow those processes. And what they need also is methods and tools to verify that the product follow the requirements which they defined here. What is the production? In this here I make shorter because we're not concentrating on the production. We are putting more on the design side. We are talking about design for reliability and maintenance. It's been design, so we are concentrating more on the design phase. But anyway, the production, what they are looking for, scalable. It means that they can produce many parts quickly, fast, and reduce the product cost. Because sometimes the production cost is high, and they want to reduce the cost. Then comes the customer service. What they want, less returns. They want to have the best maintenance concept with the minimum lifecycle cost with the highest availability. Availability, operational availability, you will see that during my presentation. It's A sub O, operational availability, remember that. So in order this will be successful, what we need, the responsibilities for the management, need to support the engineering, ensuring the ROI, return of investment. It means that they need to allocate resources, especially money. For the money, they can make all other resources. Engineering are responsible for the functionalities, and Q and A RAMs are responsibility for the product reliability and supportability. So you see how a company works. They need to have a customer that needs a product, a good product. They can sell, they can make money, so they can make those departments and be successful for the next generation of the product. I start with an example. This is a pressure meter, a simple equipment, very simple. I will use this example during my seminar today. A pressure meter, it's measure the pressure, the air pressure. If the pressure is a normal, then the green light is lighted. If the pressure is high, the red light is lighted. Very simple. Now that company they do a lot of money, sell 5 million devices like that a year, and it's prices for for 10 euros. So they sell 50 millions per year. It's not a bad business. They don't need new feature. They just reproduce this again and again because this is used in some places which is needed. So no special or no additional feature will be introduced in the next year. So I have for you a question. What do you think should be the MTBF of that equipment? You can guess also. It's enough. What you feel? It's a should.
Once a year.
Once a year. Okay. A year it's 8,000 hours, something like that. Okay, make it round 10,000 hours. Okay, rounded. So you think that if a device that this example is followed for large quantity in the field. There are systems that are few systems in the field, and then of course we need to think about those products differently. So in this case, we are talking about a product that is very cheap. They sell it in a lot of quantities, and of course the company wants to make money. Let's see what happened if MTBF is 10,000 hours. Okay. So we have 5 million device sold in the previous year. So we have 5 millions multiplied by the hours per year. We get 43 billion hours operating hours for all those 5 million products. So if we take this number divided by 10,000 hours every time, so we came up to 4.38 million failures. So this means they have a failure, and the company need to replace it because the maintenance or the warranty model here will not be to repair that item. It should be replaced by a new one. So they throw away the faulty, the customer come with the faulty one and get a new one. So the manufacturer give the customer a new one for free. So, but maybe some of the failures will be before the end of the first year, some of the failure after, and but if the customer give, if the manufacturer give a guarantee of 5 years, for example, most of the failures will happen in the 5 years. So he will lose 43 million euro per year. So if he sell it for 50 million, so he get only 7 million from those 50. So it's not so good. So I tried to build up a table which goes, the first line represent the 10,000 hours. So we are losing 87%. Now, if we take 90,000 hours, about 10 times, we are reducing the loss to about 10%. And we have 90, 100, and 120. It's almost around 10%. So this means that if we accept to lose 10%, then the MTBF target should be this number, around 100,000 hours. But if 10% is still too high, I have another set of numbers of 1 million, 10 million, and 100 million. So we can see that if we use 1 million hours as MTBF, the loss will be around 1%, which may be you can accept it. So you can see that the MTBF requirement is coming not from a feeling, it's coming from the business point of view. How much we accept to lose if we have a low, reliable product. In this case, a product that sold in millions, it's better the MTBF will be high. And you need to remember that MTBF is a mean value. It means that you accumulate the all operation hours, you divide it by the number of failures, and then you get the MTBF. So this is a mean value. The mean value is not exactly what we want to look to in other type of products. But in this case, the way how to define the required MTBF is coming from a simple life cycle cost or a business point of view. Let's take another example, which is a low quantity in field. So let's say a simple laptop. Laptops are sometimes sold in large quantities, but this laptop is a special one, a rigid one, so it's not sold in many numbers. So the total number of components, and I show you here a different way how to look into that. 500 components, which are divided in 380 passive components and 120 active components. Total part numbers, type of components are 150, which is split into 90 active and 60 passive. So in this case, I show you by doing some derating or stress analysis, we can improve the reliability of the product. So if we make a prediction of the product, taking into consideration that 50%, the stress is 50%, we came up the failure rate 60 failures per million hours, which the MTBF is 16,000 hours. After derating, we come up to 1.5. It's been 666,000 hours. And we have 3,000 operational systems in the field. In this analysis, we found one component which contributes to the high failure rate. So, and the reason was some kind of a problem of the fan out of that chip. So it could not support enough current, so it collapsed and failed. And we have also some problems with coils and connectors which could not carry enough current as it was planned. So if we make the calculation per year, so we take the number of hours per year, multiply by the 3,000 hours, we get about 26 million cumulative operating hours. If we divided it by the 16,000 from here, we get 1,577 failure. This laptop, the maintenance concept was to repair it, and each repair cost $100. So we are losing $157,000 per year for maintaining that product. If this calculation was done, if we are not correcting this component, or those components which have a high stress. So after we did a derating, improve the stress of the component, we come up only to 39 failure per year. Multiply by the $100 per failure, so we come up almost about 4,000 hours. What happened here, because we came up with this solution after the design was freezed, we need to do a PCB layout. We need to change, engineering change of the PCB, and the cost of that, it's not so much. So in total, we saved about $150,000 per year. So we can see that there is a connection between reliability and company profit. So when we think about the profit of the company, if we increase the reliability, we do all the needed analysis during the design, we are making the design is reliable and easy to maintain later. What are the reliability classification? What we are talking about reliability? Reliability is a general word which includes several things that we need to understand. So we have the reliability models, which can be serial or redundancy. It means the redundancy, it means something fail and you have a backup instead of it. So the mission can continue. In a serial model, that means something fail and you stop. You cannot move on. So we need to understand what is the reliability model of the product. Then we have components failure rate type. So in this case, we have constant exponential, and this is mostly for electronic components. And we have non-constant, like Y-bull, normal, bus tube, or this is mostly for mechanical components. And sometimes you can hear when we talk about reliability, about failure rate also. What this means, failure rates? It's number of failures per million hours. Sometimes in telecom, the failure rates is very small or very low number. So we cannot say 0.000 something. Then we convert it into fit, which is the number of failures per billion hours. So we have failure rate and fit. So if you see a spec, you see a document, and it's written FR or fit, you will know now what is the difference. And there are also failure types of the product. A critical failure, it's emission loss, or any failure. It's a emission loss plus for maintenance. If we're talking here about the redundant, if a backup component fail, the mission continue. So we need to understand also what is the failure type and the effect of that failure on the system. Okay, so this is a complex table. By the way, after the seminar, we shall email you, all the participants, a PDF version of the slides. The slides are a little bit modified by me before. It's been after the printing was done. So you will see some differences between what I present today and the proceeding that you have. But anyway, you will get the PDF version by email, so you can look into that. So this table, I believe, will help you in the future very much. So if we are talking about reliability, it's the probability of a product to operate without a failure during emission time. This is given in probability. It's been from 0 to 1. If we are talking about availability, is the total operation time divided by the total available planned operation time. Mostly it's a year. If it's something that runs all the time, you using the operation hours per year. If not, you need to calculate how many hours the product is working per year. The MTBF is mean time between failures. It's given in hours. Now we have MTBCF, which is a mean time between critical failures. It's only failures that cause the mission loss. And we have the MTTF, which is a mean time to failure. For one-shot devices, it's mean time to first failure. If you have a device that you use it only once, this means MTTF to the first failure. And then you have the mean time to critical failure, MTTCF, for the first failure. Here, it's also given in hours. I want to change the mode of my screen. Then we have service life. It's also given in hours. And for example, we can say 99% of all products in the field will operate without any failure for the service life period. So this is used mostly by companies that want to provide a warranty time. And they want to calculate, for example, they want to have a 3 years warranty time. And they want to have that only 1% of the product will fail during this year. And if you go back to the previous, to the first example, which I'll show you, this is the 1% which they allow to fail. So this calls a service life. You can also define as a service life instead of those MTBF and so on, all those parameters. Then you have the MTTR, mean time to repair. For a system, it's including the remove and replace for sub-assemblies. And then you have the downtime. It's mean that the time during operation when the production line is shut down. This is a definition of a production line, but if you take a system, then it's when the product is shut down. It means your system is working and suddenly it's not working. This is called the downtime. This downtime time is taking into account when you calculate the availability. So the operational time, it's mean without the downtime. I put also here all the formulas and where it's also applicable to. So you can look into that later. So now I will go parameter by parameter, which I define in the table, and I will explain and will give you some examples. So reliability is the probability of the product to operate without failure during emission time. Product reliability is built up from assemblies in a reliability block diagram. It's called RBD, or a fault tree, FTA, both using failure rates, distribution, and repair time. So in order to make the models, we have to have the most two important parameters are the failure rate and the time to repair. With that, we can build up the models. RBD and a fault tree represent the redundancy model without the logistics, assuming spares are available with no delay time. So if we want to make the calculation of the reliability and availability of the system, including the logistics, we need to use other techniques, not the RBD and FT. RBD, it's simple, that saying that the logistics is available, spares are available, and no delay time. It means no logistic delay time. And if there is no redundancy, the model is a simple serial. It's an OR gate. For the RBD, it's a serial. For the fault tree, is an OR gate. And no need for repair time, because if the system fail, now it's failed. So we are counting only the downtime, which is calculated or used by the availability. The formula for the reliability is the exponent minus t divided by MTBF. So in reliability you can get many types of graphs, and I put here several graphs that shows you the different. So if we see the reliability graph, failure density, and failure rate. Mostly they are given the same information, but in a different view. So if the system, this set of curves are for serial model, this is for a redundant system. So we can see if we have a reliability graph and we see that the slope is high, it means it's goes down directly without any change. This is a serial model. If we have something like that, which start straight and then fall down, this is a redundant model. So what we want to show in this example, that from the equation that we have seen before, that 63% of the failures will occur before the MTBF time, and 37% of the failure will occur after that. Now, if we look into the failure density, we can see, and for the redundant, it's something like that. And of course, the failure rate increases over time for the redundant. So you need to remember, in serial models, you are allowed to sum the failure rates in order to get the result. If it's a redundant system, you cannot add the failure rates, because you come up with a failure distribution, and you need to have a tool that is able to combine the two graphs together. It's not a simple add of the numbers. Here you can see you add the numbers, you get a straight line. Here it's not. I will show you an example. So reliability can be calculated in two ways. It's depend of what is more easier to describe. RBD is mostly used when you need a successful pass. You can describe what is needed for the mission to be successful. So this means if you have here this model, you need a success pass from the input to the output. So and this is some kind of a backup and redundant. So you can go this way. If this fails, you can go this way. So the pass found a way to come up to the output. This means this is a successful pass, and the calculation is done based on the statistics and the failure distribution. Here you can see another model, complex. This is a network model, a telecom network. You have two inputs and several outputs. And there are passes between the input and the outputs. So, for example, if this fails here, and the pass was gone through this way, so the signal can go and this way out. So there are a lot of backups. It can be used mostly for telecom, power distribution, in anything that any parameter, like also like water and gas. For example, if you need power here, so the power can go different way to come up to the location. So the idea is if you have a power loss of one place, is to isolate it from the other locations in order not to distribute or not to disturb the distribution of the power correctly. Another way to define an RBD is Markov models. Markov models define a state of a component. It can be high, can be low. I have some examples later that will show what is a Markov. So in RBD, you have 3 levels of models, simple models like this, that you can draw it as a block diagram. You have a network models, and you have Markov models. In fault trees, it's a failure path. It's been, you define at the root what is the failure, and what can fail in order to cause this system failure. It's a different way, so a way of thinking. So here we are talking about a successful path, and here we are talking about a failure path. Mostly it's done for safety. In safety, we define something which is a danger. People can be killed, or an equipment can be burned out. So we want to define what are the failures that can cause this disaster problem. And then we build up the failure tree, and we are using gates, OR gate or AND gates. I will show you later. And this is, we have 2 ways how to present it. One is the Explorer view, like in the computer that you see Explorer, and the traditional view, which you see like blocks and gates. So this is the system event, and this is an end, and this will occur if this and this will occur. This is an OR gate, and this failure will occur, or this, or this, or this will occur. And the program calculates for you the probabilities to the top, giving you the probability of the disaster failure. Another way to see it is the bus tube, but the bus tube is not representing exactly the product reliability in one point. This is represent the product reliability on life. So when you are introducing a new product, so early phase is this one here. So this means the failure rate, this is the life here. The normal life can be 5, 10, even 20 years. It can be not exactly as a straight line, but it can increase slowly. But the idea is that after a year or 2, you stabilize your product reliability, you improve it, you reducing all design errors and all initial problem, infant mortality. And then you start with normal life. And then after a period of years, the product goes into wear out period where the failure rate increases. This is an example of a neon lamp. And This example is 8,000 hours life. So until about 5,000, no failure will be. And for 5,000 to 10,000, there is the middle of the mean value is 8,000, all the failure will occur. And I have here also, again, a question for you. If we have a system with one resistor of an MTBF of 1,000 hours, what will be the MTBF of the system? It's very simple, 1,000 hours. Now, if we have a system which have two resistors, and I say resistors because this is electronic component, the failure rate is constant. I have a system with two resistors, each resistor MTBF of 1,000 hours. What is the MTBF of the system of two resistors? Someone need to answer.
The two resistor is in series, in parallel,
In serial.
series. You say 500.
How much?
One is 1,000.
Yes.
Two is 500.
Right? Okay. Correct. Now I have another system. Okay. The other system includes two lamps. One lamp is 8,000 hours. It's simple. One lamp, 8,000 hours. Now I have a system with two lamps of 8,000 hours. What is the equivalent MTBF of that system? It's a tricky question. But this will give you the idea how to think about MTBF and it's also 500 or what? Or it's another number?
Depend on the purpose of the lamp. No?
The what?
Depend on the purpose, the usage.
Yeah, you use it in the office.
So one failed, the second one still working, so okay.
Excuse me?
If one failed, the second one still working, so it's still okay.
No, but you need the two.
You need to, okay.
It's also a serial model. Okay. So since this is a tricky question, I will answer. Okay. It will be 1,000 hours, not 500. It will be the 8,000 hours, not 4,000. Half it was before. And why? Because the resistor behaves as an exponential, and the failure rate is constant, so we can use it. But in this case, the failure rate is not constant. It follows a normal distribution. So if you remember, I was talking in redundancy. If you have different failure rates, you cannot add or use a simple model. I used here a simple normal model, but if it's a Y-bull or a log normal, it's much more complicated, and you cannot say two systems of two lamps of a Y-bull, which the mean value is 8,000 hours, so it will be also 8,000 hours. No, they will be different because the Y-bull model, the shape is different. And I can tell you a story from our office. In our new office about 10 years ago, we have about 1,000 neon lamp in the office. And of course, when we built up the office, everything was new. All the lamps they put in place. And I knew about this model, and I was waiting 5 years. Okay, 5 years it took about the same the lifetime of the neons, and we start to see around 4.5 years, a few lamps start to burn out. Around 5 is most every day another lamp, like that. So when we finished the 5th year, we replaced the whole lamps in the office. So you can see that the failure density, or when the failures happened, is around this number. Exponential, you don't know when the failure will be. Then it's a random. We call it also a random failure. It can be from now until end of life. You don't know. So when you are talking about MTBF, you need also to ask or to know what is the distribution of the MTBF and the failure rate. Okay, we talked about reliability. Now we are talking about MTBF. MTBF is the mean time between failures, present the average time between any failure, critical system failure and non-critical maintenance call of a repairable and non-repairable product given in hours, cycles, miles, tons. It can be not only hours. In some places like trains, they're talking about miles. In production lines, they're talking about tons of products they produce, the chemical. They don't care about how much time it took. They care about how many tons of this chemical. Or how many cycles in other type of products. If we take the total operation time of all products in field, dividing by the total number of failures, we get the MTBF for exponential. If not, we need to use a model. So this means that if the system is not behave like exponential, we need to use other techniques in order to define what is the failure distribution of the field. So let's say that we have that office and we collect the failures. So we can see for the first 4.5 years, no failure. And so between 4.5 and 5.5, all the failure occur. So we can see that everything is there. So we cannot take 10 years divided by the number of failures, because then we are not correct. So we need to have special tools, special mathematical tools that takes the scale of the time and when the failure occur and come up with the failure distribution. This is done by the field data analysis, which I will show you later. So MTBF is a common described as a failure per million, a failure per billion. We talked about it already. And MTBF built up from a serial model in RBD. It's OR gate or FTA using component failure rates and distribution. So if you have a distribution, the RBD and the fault tree should be able to use this distribution in order to make the correct calculation. So what are the types? Exponential, the failure rate is constant. We call it also random, not dependent time. So sometimes you will hear it's a constant, sometimes it's a random or exponential. All those names means the same. So the product MTBF is the sum of assemblies failure rate. The failure can occur in any time with the same probability and not useful for preventive maintenance. Why it's not useful for preventive maintenance? Because if we are talking about mean values, which is the MTBF, we only make the maintenance of the 5 years or the 5,000 hours. We don't do that before. So what we want to do in the preventive maintenance is to replace the component right before it starts the failure rate to increase, not in the mean values. We want to replace it before it starts to increase. So this is why the MTBF is not used for preventive maintenance. If it's exponential random, we don't do any preventive maintenance because we don't know when the failure will occur. So if it's a random, it's not for maintenance, but if it's a Y-ball or log normal, then it can be used for preventive maintenance because we know when the slope start. I need to change the The problem is that I don't see the cursor on my computer. I need to look there. So, so this is why I am looking how to make it. If I put the cursor here, you don't see that. So it's okay, it's not working anyway. I will continue this way. Okay, for MTBF prediction, we have two ways to come up: by prediction or field data. The predicted, we divide it also in two categories, for electronic circuits and for mechanical components. For electronic circuits, we can use the fixed trace or CARE, is one of our products. And the prediction method are Mill Handbook 217, Telcordia, Siemens model, IEC 62308, FIDES, which come up with a constant failure rate and exponential distribution. Someone is familiar with FIDES model? Who is familiar with the Mill Handbook 217? Just raise a hand. No one? Okay, anyway, when you develop a new product, you want to predict the MTBF or the failure rates with the distribution of the components building up your product. So there are some standards in the market that developed by mostly by the US DoD, like the Mill Handbook 217, and there are others. In Module B, the next session, I will talk more in details in those models. But you need to know that for new designs for electronics, they are standard in the market, and they are used to predict the failure rate. Now, for mechanical components, since the failure rate is not exponential, there are other models and completely different. The models, the failure rate or the failure distribution and the failure mechanism of mechanical components are different from electronic components. So the standards are completely different. And there is a main standard, I think it's only one, it's NSWC 98. But this standard generates only the exponential distribution for the mechanical components. And engineers need to understand that this is exponential and use it and translate it into a non-exponential distribution. So what we did, BQR, we developed a tool called MRS, Mechanical Reliability Simulation, which generate the failure rate and the distribution for mechanical components. This will be shown in Module B after the break. And we can calculate the MTBF also based on the field data. So we are summing the total operation hours divided by the total number of failures using a distribution fitness. The result for each component is the failure rate distribution with the parameters. Here you can see that on the left side, this is a sample log file of field failures where every line represent a failure, starting with which system, what the serial number of the system, where its location, what it was on and off date and time, why the system was shut down because of failure or a preventive maintenance or dead on arrival, and when the maintenance starts and when it stops, and what is the off description, it's been the failure mode of the failure, and then what we have been replaced. Are you familiar with LRU? Someone know what LRU? Okay, LRU is line replaceable units, which means what you replace in the field. If you have a product in the field, what the technician are replacing in the field. SRU are shop replaceable units, those assemblies that are replaced in the shop. And we have a component. So we have 3 levels of failure. So we're starting what is the LRU replaced in the field, what is the SRU replaced in the shop, and which component is replaced internally in that assembly. So every line represents a failure with the full description of what has been failed from LRU to component. Based on this data, it's a failure log. It can come up from a ERP or a SAP or any other tool. Goes into CAF, that's computer-aided field data engineering, which analyze those field failures and come up with the distribution. You can see in this case, this is a Y-bull with 84% fitness to Y-bull, and you see the parameters of the Y-bull. In this case, this is a log normal, again with the parameters. So with a special mathematical model, you can analyze those failures and come up with the failure distribution for the components. And of course, you can have the tolerances of with all the parameters of the distribution. It's a one-sided, two-sided. Now, it is very, for data collection, for companies that are designing products and want to improve their reliability and maintenance, we recommend to collect field failures. And also to collect it properly. It's mean for repairable items, you should use serial number of the assembly. If you are not collecting or recording the serial number of the assembly, you are losing the ability to trace the history and to come up correctly with the failure distribution. And need also to classify the causes of the failure to avoid non-relevant. Sometimes there are failures or replacements, we call it, in the field that are not related to really reliability. For example, the technician is not trained enough. So he just come and instead to locate exactly the assembly which is failed, he replaced 12 assemblies, sent back to the lab the 12 assemblies. Then those 12 assemblies are coming to the lab, 11 are okay. So, but this failure come into the statistics. So we need to avoid those assemblies that are coming and they are okay. We call it no failure found, and with the fixed trace, we found also a way how to reduce those NFF. NFF is no field failure. No failure found in the field. In some organizations like telecom, large companies, the rate of the NFF is around 60%. So think about they replace 100 boards in the field, 60 are coming to the lab, and they are okay. So they put them back in the stock. So they need to fill up a lot of assemblies in the pipeline. This costs a lot of money in order to support the maintenance with those assemblies. So the idea is to reduce the number of no field failure, no failure found. Okay, now with the MTBCF. MTBCF is the same as MTBF, except that we are taking into account only the critical failures, which causes loss of the product functionality. For example, if you fly an aircraft, if the entertainment system fail, the aircraft will continue flying. But if one of the engine will fail, it's risky of the flight. So in this case, we are putting in the MTBCF for the critical, the engine, and all those assemblies which are needed for the aircraft to fly. All other parts in the aircraft which are not needed to complete the mission are excluded from the calculation. So everything is listed in a serial model, but every assembly in the serial model can be redundant. It can include redundancy. If all assemblies are needed for the mission, so this is MTBCF equal to MTBF, so this is a serial model. And again, MTBCF is calculating using RBD. So if we look into how it's look like, so this is the MTBF for the serial model. We need all the assemblies are calculated in the formula, but for critical, we don't need this and this one. For example, this is the video system in the aircraft. So we just take it out in the calculation, and we calculate only those 4 assemblies. MTTF, it's a mean time to failure. It's for a non-repairable product. It's a one-shot device with a constant or non-constant failure rate, or a mean time to first failure for a repairable product which is non-constant failure rate. It takes more time for the first failure to occur because the components are new. It makes less time for the second and on. So when we are talking on the first failure mostly will take more time. The MTBF, the time until the first failure is longer than from the first to the second, and so on. When we are increasing the number of failures, the time is going in shorter. So sometimes we need to know what is the time until the first failure. So, and critical and non-critical failures are considered. And again, MTTF is calculated by using RBD. MTTCF, same as MTTF, but for critical only. Critical causes losses of the system function. If all assemblies are considered critical, then MTBCF equal to MTTF. And it is again calculated by RBD. Downtime. Downtime is of a product is the time during operation when the system is not working due to a failure, preventive maintenance, or inspection. Downtime lengths depend on the maintenance, how much time we need to maintain it, to repair it, And this includes also the detection and isolation time, waiting time for a spare, replacement or repair time, testing after repair. And the downtime does not include planned standby time. It means if you need to standby, to make a standby, it's not taken into account because this is part of the real operation. You plan your product to have a standby before it's operate. Now, in this case, the downtime is calculated by the APM optimizer. Until now, we talked about MTBF, MTTF, all those MTXF. It can be calculated by RBD and fault tree because we are not talking about the logistics. From now, from the downtime, we need to use a more sophisticated tool which will take also the logistic effect, and then we are using the APM optimizer. MTTR and MCT. So the mean time to repair is the average time needed to repair a product, taking into account the failure rate of sub-assemblies and the maintenance time. The maintenance time is the total time of a sub-item replacement, including removal assembly, preparation, isolation, alignment, and checkout time. Now, MCT, sometimes you can see an MTTR and also a requirement for MCT. MCT is the maximum correction time to complete the repair task with a specific confidence probability, assuming long normal repair time distribution. So what we want to say that we will be successful to complete the maintenance task in 1 hour in 90% confidence. So it's not only the MTTR, it's also the MCT, the maximum time, because sometimes we want to know what is that maximum time to see if we have enough time to complete the maintenance. So if the MTTR is low, the MCT can be high, but in totally we need to check that the MCT fit into our mission phases or planned time for maintenance. For example, if we have only 8 hours a gap, and the MCT will be 12 hours, so, and we say 90%, so in 10% of the times, it will exceed the 8 hours. So we cannot do something like that. So it's been 10% of the times, the maintenance cannot be completed. So we need to take care about that. Service life. Service life is the period where the failure rate is very low, and after that period, the failure rate starts to increase, given a confidence probability. The service life is used to define warranty periods. This means that if the confidence probability, for example, is 99%, only 1% of the times of the items can fail during the warranty period. This is a different calculation than the MTBF. It's used different techniques, and this is it's better for the manufacturer when they calculate from themselves. They want to know what is the service life in order to provide 1 year or 5 years warranty for the product. If they see that the service life cannot exceed 2 years, they will not give the warranty above the 2 years, so they want to keep it in 2 years. For them, it's good because the warranty period is mostly free of failures. All the failures will occur after the service life. This means the customer, in that case, if this is also the technology life, for example, your mobile, your laptop, your equipment, the life can be 1 year, 2 years. So if the manufacturer gives you 5 years a warranty of a telephone, you will never use it. So no one is used the telephone 5 years. So if you use try to use today a telephone from 5 years ago, I think it's not working even today with the new technologies. You use something small and it is very strange. So what the manufacturers like is to design what is the service life. So the reputation is high because the product is not failing, and all the failures after. Then when the customer see you have a lot of failures after the warranty, he goes to buy a new product. And that's exactly what they want. They have that time also develop the second generation of the product. So they can move on let's say companies, they don't want to sell a product that the customer buy it once and it works forever. They want sometimes it will to limit it. But in other cases, I know for different systems, 2 or 3 years or 5 years, it's not enough. You need 20 or 30 years. So this is a different story. What I'm talking about, the service life mostly is for the commercial parts. It's not used so much in the defense because they don't have a service life in the defense. Availability. So it's operational availability, A sub O, is equal to the net operation time without downtime divided by the total useful. AO estimates the system performance and it's used as a requirement for maintenance optimization. Availability is calculated by RBD if we don't want to use the logistic or the APM optimizer if we want to use the logistic structure. So what are the life phases of a product? We start with a feasibility market review. We go with the requirement, then we do allocation. It means we have the requirement and we have the main assemblies, and now we do the allocation of the reliability to the sub-assemblies to see if those sub-assemblies can fit or meet those requirements. Sometimes we have a high requirement which cannot meet. So in this case, we are implementing redundancies in order to meet high reliability or availability. Then we have the design, we do prediction. We analyze the predictions into the system level. We do integration to entire product. And here, mostly the design is freezed. We go to production. Now the product is in the field, and we collect, analyze data. And what are the RAMS analysis types? We start with the allocation. So we are using a redundancy. And we define the requirements, the RAMs, reliability, availability, and maintenance requirement for every assembly. The component failure rate prediction, we calculate the MTBF using for the basic elements, for the components. The RBD describes the success path of needed assemblies for product operation. Now you are more familiar what I am talking about. Then is a new analysis which I didn't talk about yet, is the FMEA and FMECA. It's the effect of component failure modes on the product behavior. This is a bottom-up analysis. The stability is the ability of the built-in test circuits to detect and isolate failures. The fault tree analysis is to describe the causes of an unwanted system failure. This is a top-down analysis, so you can see the difference between the FMEA and the fault tree, and also the RBD. Safety, it's defined the failure which affecting human and environment. MTTR, the mean time to repair. The stress analysis, check if components are working in parameter safe area. Thermal analysis is calculate the temperature rise of components based on internal heating and nearby. Schematic modeling, this is a new analysis which we are introducing, is to detect design errors in schematic drawings. Life cycle cost, sparing to availability or sparing to confidence. Now, you know what is the difference between sparing to availability and sparing to confidence? I can find in many specs that sometimes is that. So the definition is for strength availability is that the asset should be available. So you need spares in order to support the asset to be available. It means the entire product or entire system should work. So how many spares you need to support that concept? And the strength to confidence is completely different. Is the availability of the spare in the stock. So if you go to the stock and you find the spare part, so you see that there is no connection between which I go to the stock to find the spare between the asset. Mostly what happened in the sparing to confidence, there are more spares calculated than into the spare to availability. So, and the spare to availability is better for us because we are not interested to build up a big stock. We want to keep spares to maintain our asset, not to maintain our stock. So I recommend you to use only the sparing to availability, not to use the sparing to confidence. Now, sparing to confidence is a simple Poisson calculation because it's simple. Sometimes it is used. Sparing to availability is much more complicated because you need to use some kind of Markov chains. So you have a stock and you are using one spare, one spare, one spare, and now you're going back. So the calculation is much more complex, but more real. Lower is level of repair analysis. This means if you want to repair or need to repair the assembly, or to throw it away to buy a new one, or to take that assembly and to disassemble it to smaller assemblies internally down to components. So what is best to take a computer and to just throw it away and to put a new computer with a box, or to open the computer and to replace the memory, to replace the CPU, or replace the power supply. And this calculation is depend on the requirement and on the concept. Sometimes it's better for the asset to have a spare PC, complete PC, because this is done quickly. You can just replace it. Or if you have time, you can just take the PC and now try to repair it. Another concept that you take, that you have a new PC, you just replace it as a full PC. You take the faulty PC to a lab and then you repair it. All those kind of calculations need to be taken into a model and to find which is the optimal solution. Then we have the preventive and predictive maintenance optimization. What is the difference between preventive and predictive? Preventive means that I will change the assembly every year. It does not matter what happened, I will replace it after every year. Predictive maintenance means that I will measure something. So think about a fan, or a bearing that moves all the time and make noise. When it's new, the noise is low. So this means okay. But this bearing can sometimes go fast, sometimes slow. So we don't know exactly when it finished the year how much this bearing was running. So if now we are coming and we measure the noise of the bearing, if the noise is low or below a threshold level, then we continue to the next year. And the next year we are measuring it again. So in this case, we can find that for expensive component, by doing the predictive maintenance, we can make more usage of the component by checking the state, and in this case is the noise of this bearing. The last one is RCM and MSG3. So those two are a workflow for the process industry and aerospace to check and define maintenance procedure. So mostly those two analyses, it's done by a design review. In this design review coming some expert that knows the product. Everyone described his experience with that assembly. And based on the discussion on that design review, they are coming and say, okay, this assembly will replace it after 3 months or after 6 months. Or we don't do any preventive maintenance, we just keep it running, and when it fails, we replace it. It goes run to fail. So this is analysis, is a time-consuming analysis that it's done by design reviews of the team. It's a lot of time. What we did with our APM optimizer, we automate that process. So by only describing the system or the product tree or the maintenance tree with the parameters, the tool will give you automatically what is the optimal maintenance concept. Now, for every analysis here, you have to follow with a document after. That document should have followed by a plan. So before you go to do those analyses, you have to have a plan. And in the plan, you need to describe the task name, the description, the quantitative requirement, how to implement it, methods, tools, interface with engineering, and responsibilities, and a timetable. So every project that you support is the design for reliability and maintenance, and you are doing such analysis, you will need to come up with a plan. Every analysis, sometimes some analysis you don't do. For example, the safety analysis you don't do if you don't need. Or you decide that you use RBD instead of a fault tree. So your plan should reflect what type of analysis you are doing and a plan how to do that. This means that the management, other engineers in the team, they know what they need to do. So if we are looking what we are introducing design for reliability and maintenance in the design. So you see the design, you see the fixtures which screen out design errors and stress errors, then MTBF, FEMICA, and testability, and in parallel can be done either safety, RBD, or fault tree. This is the reliability part, the RAM, R. And this is the maintenance part. We're starting with the APM optimizer. We build up the lifecycle cost model, and then we're starting to optimize the model for level of repair analysis, preventive maintenance, and all condition with the inspection, the predictive maintenance. Then we can do either strength availability, strength to confidence, which I recommend to do only strength availability, and also resources to availability. This means how many technicians you need, how many materials you need, how many test equipments. You can share the test equipments. At the end, we perform a life cycle cost to show that the cost was reduced and the availability was increased. This concept then, the final maintenance concept, is transferred to the ERP, which will maintain the maintenance concept in the field. For example, it will order the correct spares when it's needed, for example. It issue a maintenance ticket to the technician when the preventive maintenance optimizer recommend. Now, if we go to the design for reliability and maintenance in the service, so we have this loop. So now we are running the product in the field. We have the maintenance activities log. And then we analyze it for system and maintenance improvement. And at the end, we get the field MTBF. Now, instead to have from here prediction, we have now field, and we can run the APM optimizer again now with the field data. So during the years, I can use the tool in order to check my maintenance concept, and now to improve it based on field data. You can see that as in a general view. You have a design engineer, running with CAD tools. You see here the care, the fixed stress modules, analyzing. Everything goes into a core database. Then you have the APM optimizer with the expert. This person is you. And you are providing a recommendation to the designer how to improve the product. So this is a cycle in the design phase. Later on in the field, when the product operates in the field, you have field engineers that are managed by the ERP system. We have a small utility reliability analytics that takes the field failures and translates it into failure distribution. This goes into the core database. And now instead of prediction, we have field data. We can optimize the maintenance concept here, providing the technician and the ERP system change in the maintenance concept based on the field failures.